We have audio. Excellent. Thanks very much, guys. Let's make a start. So today, the topic of the virtual tutorial is going to be on using CrayPAT for performance analysis on Archer. So the title on the website appended to that, a case study. So I think as I've been preparing this, I'm not going to go too much down a specific case study on a specific code, because I think that would be not so relevant to the complete range of people who will be listening. But I have got examples done using a specific code in Archer. So what I really aim to do is to show people what CrayPAT can do, some basic examples of how to use the tools, the kind of information that you can get from it, the kind of things you can learn from by using it, and give you pointers to finding more information if you want to go any further with it. We can do questions as people go along. If you have a question, you can put it into the chat or raise your hand virtually. I will try and take them as we go along, or you can ask questions at the end. Okay, and like all the other Archer training material, feel free to reuse the slides here, which will go up on the website after the virtual tutorial, subject to the license. So, an outline of what we'll cover, a very brief overview of CrayPAT, what it's for, what it can do, and then I'll take you through using the various tools that are part of CrayPAT in a kind of order of increasing complexity and power of the tools. So from perf tools like doing sampling and tracing, which is the kind of bread and butter of what you can do with CrayPAT, using the GUI, and also finally using the CrayPAT API to instrument your code. And a lot of the information that I'm going to go through today, you can already find similar things on the web. So the Archer Best Practice Guide has a section on performance and profiling. One of the subsections of that is CrayPAT, and so that gives you some good steps to walk through there, using CASTEP as an example code in that case. Cray have a document on their docs site, which they update with each release of the CrayPAT toolkit. It's kind of pretty much the Bible as far as getting information on the tool is concerned. There's an online help. Once you're logged into Archer, either you can use standard man pages for each of the individual tools, or there's also a very useful little utility called Pat Help, which is a kind of command line driven, menu driven documentation system for CrayPAT. And last year, as part of the Archer training, we ran with the Cray Center of Excellence a Cray Tools course, so you can find some very useful, actually more in-depth information than we're going to be able to cover today on those pages as well. So just to begin with, I think it's worth considering why and who might want to use profiling tools. I mean, I think traditionally code profiling has been something which is considered to be part of a developer's arsenal of tools, because they care about understanding how the code that they've written performs, how it can be improved, thinking of things like the communication patterns, which parts of the code are taking up time, and in a parallel program on different parallel processes, which ones are taking more or less time, so where load imbalance might occur. And so really they're using it, would be using it traditionally as a way of directing their development effort to the areas where there are problems. So using profiling as a kind of measurement tool to help you concentrate your development effort. I think also profiling can be of use to users. I think it's important that users of HPC machines understand why their code performs in a particular way, why it scales well or not so well for any given problem, because we want people to be able to make the most efficient use possible of the machine. Obviously, many sort of mainstream package codes, for example, on Archer, provide some information. For example, at the completion of a job, they might print out a sort of timing report of where time has been spent in the code, and that's quite often in maybe more sections that are appropriate for that particular code to be more understandable to a user. But if you don't have that, or you want to get more detail, then actually using a profiling tool is a good way to do that, and it's actually not too difficult, and hopefully can help understand whether what they're trying to do in terms of the number of cores that they're running or the choice of parameters for their simulation is a good choice, or if not, how to improve it. So I hope this tutorial is intended not just to be for hardcore HPC developers, but it should be accessible to anybody. Okay, so back to CrayPAT, which is the tools that we're going to be looking at during the tutorial. So CrayPAT is Cray's proprietary performance analysis toolkit. So really it's there to serve one purpose, which is to help people to measure and to understand performance of parallel programs running on Cray systems. So among some of the many things that it can measure, it can work with programs written in a whole bunch of different parallel programming languages or using APIs for communication. These lists are not exclusive, but it covers most of the mainstream things and some of the less common things that you will see on Archer. And they also have support for GPU programming models, for CUDA, for OpenAC, for their GPU machines, unlike Archer, obviously. So we'll just concentrate on the CPU and MPI parallelization features today. They also support for profiling the performance of particular numerical libraries, including the kind of standard linear algebra, BLAS, LAPACK, ScalaPACK stack, and also some of the other more common scientific libraries that get bundled in the Cray software install, like PETI, as well. Also a bunch of I/O, both serial and parallel I/O libraries, including MPI I/O, which is obviously a subset of what can be profiled via MPI. So just to give you a feel for how it might compare to some other tools, some of which are available on Archer, some of which aren't. This is just my opinions, having tried a few of these things out in the past. So I think some of the advantages of CrayPAT is essentially it works out of the box. It's a pretty seamless experience. This is the positive spin on the fact that it's a Cray-only product. It only works on Cray platforms. You can't take it anywhere else, but on a Cray platform, it works very, very well. I think it has a nice, as I try and show in the structure of the talk, various levels of detail. So you can start by getting some very basic information about your code, and then you can gradually go deeper and understand the performance as you require, essentially. And at the far end of that scale, there's really very extreme customizability if you know what you're doing and know what you're looking for. What I would say is the command line interface, the tools that you use on the command line in CrayPAT are very good. I think the GUI is not quite as good as, for example, with Alinia's map profiling tool, for those of you who've used that. But then for those tools, for map, the GUI is the kind of primary interface. And I think for CrayPAT, the command line tools are in the primary interface, and the GUI is kind of an add-on. So that kind of goes some way to explaining that. So the major tools that go into CrayPAT, which we'll cover the use of as we go through the tutorial. So the first two command line tools, so pat build is used for instrumenting existing programs to allow you to gather profiling data. So that's a build tool, and then pat report is the report generator tool. So it takes data that's come from profiling runs using a binary that you've instrumented with pat build, and then generates reports in text format that you can read from that. So those are the two things which we'll use quite a bit. Apprentice 2 is the CrayPAT GUI. So towards the end, I'll show you a bit what that looks like as well. And then one final thing, which I'm not really going to cover as part of the tutorial, but does come as part of CrayPAT, is a tool called Reveal, which is a much more fully featured GUI for doing. It works only with the Cray compiler. It has some. It's very tightly coupled with the compiler environment for getting feedback on what optimizations at a kind of line-by-line level are having what effect on code performance. So it's certainly from the talks which I've seen from Cray on it, it seems to be very good for doing kind of single node type optimization on a very detailed basis. Let's say it's only works at the moment with the Cray compiler. And it's a kind of preface to doing any profiling job. It's always a good idea to choose a suitable job, under the following criteria. So really, you're trying to understand the behavior of your code under real-world conditions. So there's no point understanding some problems that might exist in some test job, but aren't a real-world problem. You're trying to solve real-world problems for real-world applications. But the caveat to that, of course, is if your real application takes 12 hours to run, you want to be able to do your analysis on a much shorter job for a couple of reasons. One, to avoid generating incredibly large data files during the profiling job, and you don't want to waste AUs. I mean, there's no point doing profiling, which allows you to understand how your code behaves and speed up by 10%. If you've had to run it several times, you might as well just done it the first time slightly less efficiently. But having said that, it should be reasonably short. It doesn't need to be long enough that it is kind of representative of what happens in the long run. So if there are special things in your application that happen once at the beginning, once at the end, you need to run for long enough that they become proportionally less important. And it can certainly include all the aspects of a normal job, including file I/O and things like these, because these are often areas where performance problems, of course, could occur. So the example that I'm going to use to kind of illustrate the use of the tools in this tutorial is the CP2K application. So this is an atomistic simulation program used for DFT and other models in atomistic simulation, very popular on Archer. And the particular test case I'm going to use is what's called H2O64. So this is a small molecular dynamics simulation of liquid water. So 64 water molecules. And so this benchmark has been widely used for measuring the performance of CP2K. It's now on the small side, certainly for the kinds of systems that people would run on Archer. It only does 10 molecular dynamic steps and takes about 80 seconds just using a single node Archer. So it's quite useful for generating short traces just to illustrate the tools. If you actually want to profile CP2K for real user jobs, you might want to look at something with a larger number of atoms and doing some more advanced techniques in CP2K. Okay, so having introduced the tools and the kind of things you need to think about to set up for profiling, I thought I'd run through the kind of workflow that CrayPAT lets you do. So starting from the top, the first thing you're going to do is you're going to build your code that you want to do profiling with. And there's a subsequent step to that using the PAT build tool that I mentioned earlier. You're going to build yourself an instrumented binary. So this is a program which has some additional code in it to generate profiling information on the performance of the code. And then you're going to take that instrumented binary and you're going to run it on Archer. And so in Cray's terminology, they talk about running experiments, so using your code as a kind of running as an experiment, and you get some results out of that. So you do that, and that outputs some data, which you then use the PAT report tool to analyze. This is this box in the middle here. And from here, it really depends about what you do next, of what data you've already got in your report. So you might, for example, want to generate multiple different reports from the same data, looking at different aspects of what's been recorded from your experiment, or you might decide that the data that you've got is not enough, or maybe kind of is suggestive of some particular problem, and you want to gather some more data. So you might go back and build another instrumented binary, instrumented in a slightly different way, and go around that process several times. And hopefully, eventually, you get over to the right here where you actually have got enough profiling data to allow you to identify a problem in your code that you can go and fix. At which point, once you've made your code changes, you have to go right back to the beginning again, rebuild your code, rebuild an instrumented binary, and then rerun to hopefully confirm that the changes you made had the effect that you expected them to. So as I said at the beginning, the focus of this tutorial is really on the how do you use the tools to run and analyze data from profiling experiments, not on how to figure out what the problems are and how to fix them. I mean, that's more than we can cover in an hour, and there's some good information on the Archer website already from the single node optimization and MPI courses if you want to go down that route a little bit more. Okay, so to begin with, this sort of easiest level of complexity of the tools that are available inside CrayPAT is what's called Perf Tools Lite. So this is reasonably recently introduced by Cray, designed to be an almost entirely transparent to the user way of getting some very straightforward profiling data from their program, and without you really having to do very much different. I'll go through the exact steps of how to do this in a minute. But what you get is you get a very short text report, gets dumped into the standard output from the run of your code. So you get the output you'd expect from your code, and then a little block at the end that's come from CrayPAT. And it also generates some CrayPAT data files as well, which you can then take and use with the PAT report tool. But you don't need to the simplest level. You can just run your code and read the output at the end of your output file. So the actual steps that you would need to go through to use Perf Tools Lite. So this is made available via the module environment. So module load Perf Tools Lite will set up your environment. Once you've got the module loaded, you then need to build your code. So this is worth being aware of if you think of you've already got a code that you've built and then you want to go and do profiling. You need to load the module, do a clean, and then rebuild your entire code from scratch. So everything gets built, with the module loaded, so that CrayPAT can record some data about the build procedure and insert some profiling calls and things into your code. But apart from that, I mean, you can use your normal build process, whether that's via makefile or some scripting or whatever you have. And if it's worked successfully, you should see a little message like the one here. Comes out at the end that says it's created a CrayPAT instrumented executable. In this case, the cptk.psmp is just exactly the same name as the normal binary that you'd build for cptk. It just replaces that and has the profiling code inserted into it. So once you've done the build part, the next thing is just to run your program, which you do exactly the same way as you would launch any other job on Archer via the batch system, or perhaps if you want to do an interactive batch job, using PBS is a perfectly reasonable way to do it. Your job will sit in the queue and run, and when it runs, you get all the files you normally expect from your application running, whatever kind of output it produces, the normal standard output, and then at the end of the output file, you get this little additional block which contains a few pieces of information about how your application ran from a performance point of view. So to give you some overall job info, like how long did it take, how much memory did it use, these kind of bits of information. It will give you a basic profile of the top 10 most time-consuming functions that were detected during the execution of your program. And it will also tell you some things about I/O, which files your code has been accessing, how many times, what sort of size of reads and writes were done to those files. And that data also gets saved into a .rpt report file, which is just a plain text file containing the same information as in the standard out. And it also generates a CrayPAT performance data file, so this .ap2 file format, which you can take and do further analysis on if you want. Okay, so I'm just going to step out of the presentation here and have a look. So today is a maintenance session, but with a bit of luck, the test and development TDS system is still up. So we can have some files that I prepared earlier on the machine. Okay, so So I hope you can all see that. Can we read the terminal window reasonably well? I can make it a little bit bigger maybe. Is that readable? Someone give me some feedback. Yeah, excellent. Okay, so the things that are in that directory there, so there's a batch script, which is nothing special, just pointing to the binary that I want to run, which was built with the PerfTools Lite module loaded. And it's a very short job, just running on a single node. There's also some input files and output files from CPTK, which I won't go into because they're not particularly relevant to this discussion. But also here's the standard output from the code. So up to this point, this is all kind of standard stuff that you expect to see out of CPTK. And then when you get to the bottom, this is the little section that gets added on by CrayPAT Lite here. So it gives you, as I said, some basic information about what your code was doing, how many MPI processes or threads it was using, when it was run, how long it took, and some sort of aggregate statistics about the computation and the memory usage. Then this table here, which gives you the top 10 functions according to the amount of samples, how many times it's been detected to be inside those functions during the execution. These are grouped. So Cray have this grouping of places time can be spent in your code. So user code is kind of your source code that you would have built. MPI is called the MPI library. ETC basically means things inside other libraries or places that can't obviously be identified as user code. In this example, actually, with CP2K, a lot of the time, so here over about 57% of the time, is spent in some performance critical auto-tuned libraries, and those were built separately to the main build process and didn't have the CrayPAT module loaded at the time, so they're kind of identified separately, even though they're kind of conceptually you can think of them as part of the CPTK application user code, and they get identified separately. If you were to build the whole thing with all the dependent libraries with the module loaded, they would appear as user code. It's a little bit less information available about those. And then again, some further information about the file I/O input, things which get read, and then the things which get written out. Okay, so that's the basics of what you get out of PerfTools Lite, and there's also here this AP2 file, which is the portable performance data file format that you can take and use elsewhere. Okay, so hopefully I've convinced you that using PerfTools Lite is probably not too difficult to do, and you can get some basic information out there. So the next kind of level on the sort of hierarchy of complexity and power in CrayPAT is doing sampling experiments. I kind of already hinted at this with PerfTools Lite. Actually, that's what PerfTools Lite is doing under the hood. It's doing sampling, a sort of limited form of sampling. What do we mean by sampling? What it means is when your program runs, every so often, defined frequency, which by default is 100 times per second, CrayPAT wakes up and looks at what your program is executing at that particular point in time and keeps a record of it, including which functions had been called down the call tree to get to where it's currently executing. So the idea with sampling is it's a good way to get a feel for the behavior of some code, even if you know nothing else about how it's been implemented. You treat it as a black box and not a sampling experiment. It's very, very low overhead because you're only interrupting the program 100 times a second. At least for the example I tested, the overhead was within about 1%, which is kind of about the level of noise you might expect from one run to another. And it's still slightly more involved than PerfTools Lite, but still very easy to set up and run. So here's the steps. Again, similarly to PerfTools Lite, You have to load the module before you build your code. Go through the whole build process from scratch. And one thing I didn't say before, actually, for most codes that use a make file, this is not a problem. You have a bunch of compilation steps where you compile individual source files into object code, and then you link them together into an application. But for some very small codes that people might have written, they might do a sort of monolithic compile and link step. So if you do that, CrayPAT won't work correctly. You do need to separate those two things out. So this is a technicality that it's worth being aware of. Once you've done that, so there's an extra step which uses the pat build routine tool for instrumenting your code. So if you just want to do an instrument for a sampling experiment, all you need to do is pass it the name of the binary you want to instrument, and then the -o option is the name of the binary that you're going to get out that has been instrumented, and no other arguments. Just means that CrayPAT will instrument it for a sampling experiment. So you can call the binary whatever you want. Cray have this sort of terminology where they add plus something to indicate how it's being instrumented, which is quite a useful convention. So in this case, plus samp for a sampling instrumented binary. Run it exactly the same way as you did before. Just be careful that you actually run the sample, the instrumented binary rather than the old one. It's very easy, of course, to just use the same old batch script. And once your job's completed, you don't get any additional output in the standard out. You just get these data files dumped into the directory where your job was running. So the file format that Cray used for storing profiling data is the XF file. So if you're just running on a reasonably small number of PEs, you'll just get a single XF file. If you're running a large number, I forget exactly what the definition of large is here, but certainly if you're running on several thousand or more PEs, you'll just get a directory, a subdirectory within your run directory that contains multiple XF files. So they're split up like that. And then once you have got that, you can then use the patch reports tool to pull data out of the XF files. So in this example here, just running pat report on a single XF file, or equivalently on a directory if you have a large number of them, and then just by default it'll dump the report to standard output so you can redirect it to a file. So you get your text report file which you can read. It also, as part of the process, as a byproduct of this, is it turns the XF file, which is not portable, into an AP2 file, which you can then actually take and move to another machine for analysis. So the XF files refer to system-specific data related to the object files used to build your code. So that's the AP2 file. The other thing that you get out is you get an APA file. So this is Cray's automated profiling analysis, and I'll come on to later when we talk about tracing experiments what that's used for. But that kind of feeds forward into the next step of the process. Okay, so that's the basics there. So let's go back onto the terminal. We'll have a look here. So there's a sampling experiment. Okay, so same kind of things. Again, as before, we're using the sampling instrumented binary rather than the one I started with. You can see there you had the XF file, the AP2 file that was generated by the pat report process, and the APA file that I just mentioned. So to give you an example of what a patch report output looks like. So this is kind of similar in feel to what you got from CrayPAT Tools Lite, but giving more detail. So it's just running with the default report options. You get a number of tables get generated. So it tells you exactly what's going to be included in that table. And so the first one is similar to the CrayPAT Tools Lite report, a profile by function, where all the time in your application is going. Similar thing, but not just restricted to the top 10. There's many more things there. Also, you can see there's another group there for OMP. So the binary I was testing, although I'm actually using just 24 MPI processes, has been compiled with OpenMP enabled as well. So you can see, even though we use one thread per process, there's some OpenMP calls in there some timing calls. So that was the first one, just the basic sampling profile. And then there's a second table here which actually shows which lines within which source files were identified as coming up most frequently in the sampling. And there's also some data in the third table on hardware performance counters as well. So this is really starting to get into potentially quite low-level stuff about how many operations. So this is just aggregated over the entire run. You can see how many flops are done in single precision, double precision, and instruction issue and these kind of things here. And there's also memory utilization, cache hits, and these kind of things. So that's just with the sampling experiment, you can only get hardware counter information aggregated for the entire run of the code. If you want to break that down further, you need to go on to doing the tracing experiments. Okay, and then the fourth table here is again just showing some information about what was going on the different processes, the amount of memory that were used by them, and the amount of wall clock time they're used. So here, this way of displaying data is MMM is min, mean, and max. So that'll be this is sorted by time here. So that's the max, the mean, and the min there. Okay. And then there's lots of extra diagnostic stuff at the bottom. And so that's the kind of thing you can get just from the basic reports. You can also do additional kinds of reports like the call tree reports, which takes the sampling information and presents it in a kind of hierarchical fashion. So this is kind of shows what's calling what. So these things which are showing up in the profile is reasonably expensive. It shows which routines in the user code called them and which they were called from. So you can use that to kind of identify in a more sort of schematic way where the time's going in your program. Okay, so that's sampling, and a very brief look at the reports. As I said, I didn't really intend to go into exactly the details of what all these things mean and kind of what information you can derive from them, but just to give you a flavor of what you can generate and how to do so. So the next sort of rung up the ladder of complexity is doing tracing. So in comparison with sampling, which just interrupts a particular fixed interval to check what's happening any instant in your program, tracing inserts what are called intercept routines at the entry and exit points of subroutines in your program. So it can record precisely the amount of time spent in each individual call of a function. It can record at what time those function calls were made, so you could generate a sequence, a kind of timeline of events in your program execution. And also you can record the state of the hardware counters at entry and exit of routines. That allows you to break down the hardware counter information on a routine by routine basis. So clearly it can give you a lot more information than you can just get from a sampling experiment. You can go a very, very long way with this, but it really, you have to decide what you want to trace and what information you don't want, because the amount of overhead that you get from a tracing experiment really depends on how many routines that you trace, and whether you, especially whether you trace very small routines that are called very, very frequently, can dramatically increase the overhead. So for a sort of reasonable kind of ballpark figure, you might expect a sort of 5 or 10% overhead in runtime compared to just running your code without any profiling at all. So there's a balance to be had here between getting very detailed measurements versus kind of disturbing the experiment that you're trying to carry out. You don't just want to measure. You know, if you measure, if you trace a very, very small function which gets executed millions of times, you'll see a very, very high trace overhead, so you're not going to learn so much useful about your actual program. Okay, so how do you do this? Again, very similar flow to the sampling experiment. Build your code with CrayPAT Tools module loaded. This time, when you use pat build, instead of doing the default thing, which gives you, so I'll fix that typo in the slides before they go up. So if you want to build a tracing instrument program, you have to provide some extra options to pat build. and you get yourself a new binary which has the trace intercept routines added to it. So stepping aside from the flow of what you have to do, some of the options that you can pass to pat build, so there's a really a very large variety of things that you can do here. I'll just highlight some of the main ones. So there's an option -G, which allows you to specify trace groups. So these are predefined types of routines which CrayPAT knows about. So for example, you can trace any calls to the MPI library. That's probably a good thing to do if you have an MPI parallel program. Likewise, if you already know that your code spends a lot of time in linear algebra libraries, for example, you want to trace LAPACK or ScalePACK in a parallel program. So you can use those. You can also start to trace user code functions. So there's a couple of options there. So -W just says that you can, CrayPAT will start to generate trace intercept routines in user code, and you can either use this -T option to say, I want to trace specific functions, so write them down by name, or you can say just trace everything, which I would say, use with extreme caution, because that will create a lot of trace intercepts. It will slow your code down and it will generate enormous files. So you might only want to do that if you have a very simple program that has very sort of chunky functions. So the point is there's lots of tunable options here into what you trace. It can be quite complicated. You might not necessarily know exactly what it is you do want to trace. Tracing MPI library calls is, if you're just worried about the communication performance of your code is sometimes a reasonable thing to do. So just doing pat build -G MPI. But if you're wanting to look at things like load imbalance, for example, that won't really help you very much, because all it'll tell you is some processes are spending more time in non-MPI stuff, and it won't tell you where. So this is where the APA file, the automated profile analysis, helps you. So this is the APA file, something which came out of the sampling. So actually, you quite often will want to run a sampling experiment first as a precursor to doing tracing. Even if you don't look at the results from the sampling experiment, you can use the APA file. And what it does is it basically recommends a bunch of options that you can pass to pat build to set up a tracing experiment. So to do that, you call pat build, you say $O and pass in the APA file. So the APA file just contains a list of command line options which are generated as a result of the data that it gained during the sampling process. So the default kind of behavior for an APA tracing experiment traces MPI. It gathers hardware counters using the default hardware counter group. So there's various different hardware counters you can collect. I just use the default one. It will trace any user functions which use more than 1% or had more than 1% of the samples up to a maximum limit. And it doesn't trace very small functions. So if your code is spending a lot of time in some very small functions, what it won't do is it won't trace those. It will trace the routine, the calling routine of those to avoid getting lots of trace overhead. So once you've done your pat build, either using command line arguments you specified yourself or using the APA file, again, run your code and you get the same stuff out, XF files or a directory full of them. And you can use exactly the same analysis tools, pat report, and you get the same performance portable data file out. You don't get another APA file out. That's just something that comes from the sampling experiment. I'm going to show some examples of some of the reports you can generate. But just to give you a flavor here, I mean, there's a massive amount of customizability in what reports you can generate. A good place to start, there are some predefined types of reports. The one you get by default is -big O profile, which is similar to the sampling report, lists the most expensive functions. You can do the callers and call tree reports, and the callers plus source with line numbers. You can start to look at other things like load balance, for example. So these are you can find these in the man page for pat report. There are a whole bunch of these default reports. I'll show you some of them in a minute. A nice feature of CrayPAT, I think, can help you kind of get into customizing reports if you want to. So for example, at the bottom here, if you use the dashboard profile, it tells you what individual command line arguments that default corresponds to. So if you look at that table and think, actually, I don't want the top 95% of all the time functions to be shown, I just want the top 50, then you can change that. Or if you don't care about load imbalance, for example, you can get rid of the imbalance columns, or you can say, I don't just want to have some aggregation over PEs, I want to spit out the data for each individual PE or the min, mean, and max. You can start to change these things. So it gives you a point to get into for modification. And again, you can find out exactly what these things mean by the man pages. And also alongside the tables, there are suggested options for other tables that you might want to look at, and some generic observations and suggestions section, which is CrayPAT doing some automatic analysis of your profiling data. Okay, so I'm just going to jump back into the terminal again. So here's a folder that I did earlier based on the results from the APA file. So I'm going to show you from the sampling experiment the actual contents of the APA file. So these are basically just a bunch of comments and actual command line arguments that would get passed on to PAT-mill. So it's the -GMPI, and then these -T. So this is tracing specific routines, and some of them is not tracing there. So I said they were in the external libraries that were compiled without the PerfTools module loaded. Okay, so that's basically, and so you can also go in and modify the APA file if you want to do it that way as well. So once you've done that, build your instrumented binary and run it again, you can start to generate some reports. So this is the default profiling report here. Again, as I said, it shows you a bunch of options for related tables that you can do. And this is starting to show a bit more detail. So compared to the sampling experiment, which is just saying how many of the 100 times a second did I see this function be executed, and now it actually breaks down exactly how much time was spent in each of these functions, and it can also say what the imbalance time is, so what the difference between the min and the max overall the processing element of your program, and so you can start to see some information about load imbalance there that you didn't see with the sampling report. Also with MPI calls, it starts to break things down into, for example, here you can see there's an MPI section and there's an MPI sync section. So this is giving you some information about how much time is spent actually doing communication and how much is overhead due to synchronization. So that's again something that you can get via the tracing experiment that wasn't there in the sampling experiment. Okay, the observations and suggestions section. So here it's maybe not telling us anything particularly interesting, but it will flag up, for example, if you have very poor cache utilization without even having to go in and look at the hardware counters report. You can just read the headlines from there, and that gives you some information to look at. And then this is the detailed hardware counter report. Same information that was in the sampling report, but instead of just the whole program, so the total here, it splits it up into user, main, and then individual function calls. So you can really look on a pretty detailed basis. The other thing it does is with profiling, actually CrayPAT's able to make an estimate of the amount of overhead introduced into your program in particular routines. So I think if you trace a very small function, that's something that gets flagged up in the output report here. So if you're really affecting things too badly in that way. Yeah. Okay. Okay, so moving on. So that was kind of, you can go a very, very long way with the command line tools. There's a lot of information you can mine out of your code there. But there is also the GUI. As I said, it's not as fully featured as the command line interface. You can get a lot more information through the command line tools, but the GUI does give you some advantages, and it gives you a very it's certainly easier to understand the call tree of your program in a graphical format. It can print out charts of particular data and show kind of the sort of stereotypical application traces that you might be used to seeing from other profiling tools. Actually, you don't get that by default with your tracing experiment. You have to set a particular environment variable. So by default, CrayPAT does a summarization, so it throws away some information in order to save on space. If you want to do an application trace where you can see what every process is doing at every particular point in time and where the communications are between them, each individual communication, you need to set this environment variable, and then what you get is you get very, very large trace files. So from the ones I showed you, the example so far, your trace files are a few tens of megabytes, and once you turn off the summarization, you get very quickly up into gigabytes of data. So if you're not careful, you can really run out of disk space or whatever, and these take a long time to process as well. So if you want to use the GUI, so it's called Apprentice2, the actual binary is called app2, so you can run it directly on the front end of Archer. If you're handling large files, you don't want to do that. It's going to take up too much CPU time, and you'll probably find that your session gets terminated. But what you can do, so this is the advantage of the AP2 file format, is it's now, compared to the XF, which is tied to that particular machine, the AP2 contains all the information that's needed, so you can move it off to your desktop and run the Apprentice2 binary there. And there are installers for Mac and Windows that are included in the CrayPAT directories on Archer, so you can just copy the relevant there's a Windows installer and a Mac disk image in that directory. You can copy and install on your local machine for doing analysis. So again, I'll just give you a little look at what the GUI looks like. So this is running locally on my Mac. So you can either, there's also a remote open, so you can open files on another machine, but here I've actually copied all the files I wanted already onto my machine here. So here if I just open up a PPA file, you can see a few things in the GUI. It's got a kind of headline page that tells you, if you mouse over these little information bits, it should pop up, because it actually tells me I should be informed. It's not making any suggestions in that case because I'm running on one node, but you get the idea. So this gives you the overview of what's been measured during your tracing experiment, and you can then drill down into where the time went. So in this case, I think there's a lot, as I showed before, even in the sampling experiment, a lot of the time in CV2K is spent in these external libraries. So it's maybe not, it's not a particularly interesting example, but you can see there a split between the sorting the number of calls and where the time goes. You can also access the text report. It's exactly the same information that's available via the default report on the command line. And you can do some other more visual things like the call tree here. So this the individual blocks here. So this shows some indication of load imbalance. So that I think the purple is the light purple is the min, the mean, and the max. There's a large difference between those. You can see there's a load imbalance problem. The height of a blob is kind of proportional to the amount of time spent exclusively in that routine, and the width of it, I think, is proportional to the amount of time spent in that and all its children. So you can see, and this is a very simple example, we're only tracing a couple of routines. It's not very interesting call tree to look at. But if you do a more extensive profiling, you can see all the information laid out there, and you can mouse over things and get further information, for example, on the hardware counters through that. And this AP2 file here that I opened was one which was done with the runtime summarization turned on, so you don't get the full application trace. Some extra buttons appear up here if you had summarization turned off. Okay, so the last kind of tool that I wanted to cover was using the CrayPAT API. So, I mean, actually, CrayPAT kind of internally to all these tools has a library for doing these trace intercepts, for recording all the performance data whenever an intercept is encountered. And that API is exposed to you as a programmer if you want to have very fine control over what's being traced in your application. And so a couple of things that gives you. One is that you can insert a call into your application to say, start tracing here and stop tracing here. So this is one way you can get around the problem of having expensive startup or shutdown segments in your program. You can just, in your program control flow, insert a start tracing directive or call after the initialization is completed. So the actual profile data only gets recorded for a subset of the time that your job runs. So you can do that, and then you can also define regions at a more granular level than just individual subroutines that the normal trace intercepts that get generated by PAT builds would give you. And so this might, for example, if you have a large subroutine that has multiple different loops inside it and you want to be able to break down how much time is spent in this loop and how much time is spent in another loop, then you can add these PAT region calls. So it just gives you a unique identifier and a name, and those things come straight out into the reports. You'd see them in exactly the same way as you would see a subroutine call, which had a trace intercept routine added to it by CrayPAT automatically. And there's also a Fortran version, so you can do these, put these calls into Fortran programs as well. And so once you've added some CrayPAT API calls to your application, similar to before, you can just build again for a API instrumented, I've called it here, experiment. You can also add other options. You can combine CrayPAT API tracing with automatically generated trace intercept routines for other user functions, or with the predefined trace groups like MPI, for example. So this gives you an awful lot of control. Again, I would say just be careful about putting in sort of micro regions that may get called a lot and take up very little time. You might find that you get quite a lot of trace overhead. And it's also worth mentioning that clearly once you've added these API calls into your code, you can no longer build your code without linking to the CrayPAT library. So you need to have the PerfTools module loaded whenever you build your code at that point. So you might just want to think about either including API calls in sort of debugged code, or if you're including it in production code, at least put some defines in there that would allow your code to be compiled without having the CrayPAT API in it. Okay, so that was a very rapid tour, I think, through CrayPAT. As I said at the beginning, there is the on the Archer web, or linked from the Archer website, there is the Cray Tools course, which I think was a 3-day course or a 2-day course run by the Center of Excellence, which goes through all this stuff in a lot more detail. You can go and look at the information there at your leisure. So I hope I've given you a bit of a flavour for what you can do, what the kind of processes you go through, and some of the sort of gotchas that you want to think about when you're doing profiling. So I'm going to stop there. We've got plenty of time. If people have questions, please just pop them in the chat box. Otherwise, that's all I wanted to say. So thanks very much. And just to echo the slide I had at the beginning, there's some of the places you might want to go and look for further information. So a question from Andy: can you profile memory usage using CrayPAT in a useful way? So I think the thing that you can measure is just I mean, it doesn't do leaking. I think you can trace how much memory is allocated. So that might give you a hint at a leak, but isn't necessarily indicative that memory is leaking. But if you want to do that, you're going to need to use something like Valgrind, for example, or so GCC actually now have a really nice in GCC 4.9 they introduced a thing called leak sanitizer. So you can do memory leak checking directly just with the compiler. So that's quite a nifty thing that you can use there. But I don't think really CrayPAT helps you particularly in that regard. So this is the difference between actually allocated and actually touched. I don't know is the short answer to that. If you like, I can have a bit of a dig through the manual and get back to you on that one. Which version do I find myself in? So I have to say I hadn't used the CrayPAT Lite at all, and I only really came across it when I was actually reading through some of the documentation preparing for this. I don't know how new it is. So it's not something I'd come across before. I don't think, to be honest, it gives you much different to what you get from sampling. I tend to find myself going to tracing pretty quickly, especially if you're. Sampling is really good if you've never profiled an application before. So if you just get thrown a bit of code and need to look at it, I would go for the sampling first. But once you actually want to get into the details of looking at things like load and balance, MPI performance, you really need to go for the tracing. And if you're interested in kind of serial code optimization and want to look at hardware counters, then again you need the tracing to be able to get that stuff on a per routine basis. I mean, I think my experiences for looking at the sort of serial optimization stuff with the hardware counters, I think the support they have is actually so good that I've taken code from other machines, brought it on, compiled it up with CrayPAT, run it in serial just for doing serial code analysis using CrayPAT, done some optimizations and taken it back to the machine I was actually wanting to work on. But that's, part of that's because I spent a lot of time, not so much recently, but a few years ago, I spent a lot of time doing work on CP2K with CrayPAT using the API and kind of knew the tools inside out. So it doesn't necessarily say it's better, but it was a tool that I knew at the time. And as you might have also gathered as well from the sort of opinion I was giving, is that I tended to use the command line tools rather than the GUI. It's just kind of, once you get to know the kind of options you're looking at, it's much quicker to get at the data that you want. So does anyone else have any more questions? Otherwise, we'll draw things to a close. Okay, well, we'll finish up there then. Thanks all of you for coming along, and watch out for the stuff going up onto the Archer website in the next few days, hopefully. Thanks very much.